Today, we will look at the valence bond theory. Now let us look what it means to form a covalent bond. In the covalent bond, we know that the shared pair of electrons are attracted by the nuclei of both the atoms. In order for this to occur, it is therefore important that the orbitals of the different electrons are overlapping. Upon overlapping, a new molecular orbital is then formed. There are two different kinds of covalent bonds, and these are linked to how the orbitals are overlapping. In the first case, we have the sigma bond, and in the second, we have the pi bond. Let us first look at the sigma bond. This occurs when the orbitals are overlapping on a head-to-head. The electron density is then concentrated between the nuclei. The first bond formed between any two atoms is a sigma bond, but there can only be one sigma bond between any pair of atoms. Let us consider atoms that have s and p orbitals. In this case, there can be three types of combinations for the sigma bond. The first is a s and s overlap. The second is an s and p, and the third is a p and p. For the s and s overlap, let us consider hydrogen. We know that the hydrogen has its electron in the 1s orbital. It is therefore possible that these two orbitals existing on two separate hydrogen atoms are overlapping to form the sigma bond. For the p and p overlap, let us consider chlorine. We know that the chlorine has an electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p5. Therefore, one of the p orbitals is not paired. This unpaired p orbital is then used to overlap to form the sigma bond. For the s and p overlap, we can consider the molecule hydrogen chloride. In this case, the hydrogen is using its 1s orbital and the chlorine is using its 3p orbital. Having looked at the different types of sigma bond, let us now look at the pi bonds. The pi bonds are formed by the side-to-side overlap of the orbitals. In this diagram, we see two p orbitals overlapping each other to form the pi bond. The pi bond takes place when atoms undergo multiple bonds, for example in double bonds and triple bonds. Now let us consider why this is so. In the first case, if you think in a 3D space, only one head-to-head overlap is possible. Therefore, every other bond will have to be a side-to-side overlap. For any covalent bonds, the first bond will be a sigma bond and every other bond will be a pi bond. In a double bond, we have one sigma and one pi bond. And in a triple bond, we have one sigma and two pi bonds. To look at this closer, let us look at the oxygen molecule. Here, we see two oxygen molecules coming together. Oxygen has an electronic configuration of 1s2, 2s2, 2p4. Therefore, two of its p orbitals are unpaired and can be used for bonding. One of the p orbitals is used to form the sigma bond with a head-to-head overlap. The second orbital will then only form a side-to-side overlap to form the pi bond. In this diagram, we see nitrogen, which has a configuration of 1s2, 2s2, 2p3. Therefore, it has three unpaired p orbitals. One of the unpaired p orbitals is used for the sigma bond, and the other two p orbitals are used for the pi bond. Let us now look at the theory of hybridization. The theory of hybridization is used to explain the shapes of molecules and the equivalence of the bonds used. Let us look at the problems encountered when using the overlapping of pure atomic orbitals to form covalent bond. In the first case, let us consider carbon. Carbon has an electronic configuration of 1s2, 2s2, 2p2. In this case, only two p orbitals have unpaired electrons. Therefore, it only goes to reason that carbon should form only two bonds. And we also expect that carbon would form these two bonds at 90 degrees to each other, which corresponds to the two different p orbitals used. We would expect that carbon would form a compound with hydrogen to form CH2. Yet, the simplest stable compound between carbon and hydrogen is actually CH4. And the angle between each of the bonds is 109.5 degrees, with all the CH bonds being equivalent. The same goes for beryllium, which is 1s2, 2p2. In this case, we do not expect any bonds to be formed since there are no unpaired orbitals. Yet, BeCl₂ has been found to be a linear molecule with a bond angle of 180 degrees. In order to explain the different shapes formed, we have the hybridization theory. This theory involves a mathematical exercise to explain the observed shapes that we see in the different molecules, as well as the equivalence of the bonds. It involves mixing two or more pure atomic orbitals together to form new hybrid orbitals. Well, the first thing we need to note is that the number of pure atomic orbitals used in the mixing should also be the number of hybrid orbitals formed. The hybrid orbitals formed then has a different shape and direction properties from the original atomic orbital. In this slide, we see the example of the sp orbital, where one s orbital combines with one p orbital to form two sp orbitals. The hybrid orbitals formed are then equivalent in energy and shape to each other. The angles between the hybrid orbitals are determined by theoretical calculations. And the original electrons that existed in the pure atomic orbitals are now placed in the hybrid orbitals. Singly occupied hybrid orbitals, which contain unpaired electrons, are then used to form covalent bonds. Let us look at some of the geometry of different hybrid orbitals. The first is the sp orbital. This is formed by the combination of one s orbital and one p orbital to form two sp orbitals, which are 180 degrees apart from each other. In this next case, we see the hybridization of one s orbital and two p orbitals. These will form three sp2 orbitals. The sp2 orbitals are arranged in a trigonal planar formation. What if we combine one s orbital with three p orbitals? In this case, we have four equivalent orbitals, which are the sp3 orbitals. The sp3 orbitals are then arranged in a tetrahedral arrangement. This slide gives us a summary of the different types of hybrid orbitals. It also shows some examples of the molecules that have used this type of orbitals. Other hybrid orbitals that are not discussed here include the sp3d, which is used for a trigonal bipyramidal arrangement, and the sp3d2, which is used in an octahedral arrangement. Let us now try to combine what we know about the hybridization of orbitals to look at BeCl₂. In the ground state, BeCl₂ exists as 1s2, 2s2. In order to form the bond, one electron from the 2s is now promoted to the 2p to form an excited state. We then have a combination of the s and p orbitals to form two sp orbitals. These two sp orbitals are then 180 degrees apart from each other and can be used to form a bond by overlapping with the p orbitals in the chlorine atom to form BeCl₂. This slide shows the formation of the BeCl₂. Let us now look at the sp2 hybridization, which is found in BF3. In the ground state, the boron has an electronic configuration of 1s2, 2s2, 2p1. One of the electrons from the 2s orbital is then promoted to the 2p orbital in the excited state. The 2s orbital and two of the 2p orbitals are then hybridized to form three sp2 orbitals. In this slide, we see the formation of BF3, where the three sp2 orbitals, which then form a trigonal planar arrangement, is used to overlap with the singly unpaired p orbital of the fluorine atom. Another type of sp2 hybridization can be seen in the molecule C2H4. Both the carbons in this case have a ground state of 1s2, 2s2, 2p2. One of the 2s electrons is then promoted to the 2p orbital to form the excited state. The 2s orbital as well as two of the 2p orbitals is then combined to form the sp2 hybridized orbital. This case is different from the BF3 in that the carbon also has one p orbital which is singly occupied. In this next slide, we see what is happening in the formation of the different bonds. Firstly, we see 4 hydrogen atoms using their 1s orbital to overlap with the sp2 orbitals of the carbon. One of the sp2 orbitals of each carbon is then overlapping to form a H-on overlap, which forms the sigma bond. The two singly occupied p orbitals can then overlap on a side-to-side to form the pi bonds. In order to look at sp3 hybridization, let us consider the simple molecule of CH4. One of the 2s electrons of carbon is then promoted to the 2p orbital to form the excited state. The 2s orbital and 3 of the 2p orbital is then hybridized to form 4 sp3 hybrid orbitals, which are then directed towards the different corners of a tetrahedral. Each of the hydrogen then utilizes its 1s orbital to overlap with the 4 sp3 orbitals found in the carbon. This then gives the shape of CH4, which is tetrahedral. Other examples of sp3 hybridization is that of ammonia. In ammonia, the ground state electronic configuration is 1s2, 2s2, 2p3. The 2s orbital combines with 3 2p orbitals to form 4 sp3 orbitals. One of the sp3 orbitals is now having a pair of electrons, leaving only 3 having an unpaired electron. The 3 sp3 orbitals that only have one electron then overlaps with the 3 hydrogens s orbitals to form NH3. This gives a shape of trigonal pyramidal, and on top we see the lone pair of electrons. Other examples of sp3 hybridization include that of water, but in this case there are 2 lone pairs of electrons and only 2 of the sp3 orbitals are used to form bonds.